would like to support your compression flange at this point, maybe this point, so the distance in between called LB. In this case, your concrete slab supported your compression flange at each single inch. So your LB in this case equals 0. So if you would like to, in this case, your unsupported length, your flange is supported here at this location, supported here at this location. In between, we don't have any supporting. So your distance called LB. So LB is the length between points that are either braced against lateral displacement or braced against twist of the cross section. So you can figure it out from your structure. Second term, LP and LR from table. Based on your cross section. So we have a table called design of beam. Do you remember? This table can tell you what is the cross section name. Maybe for example W20 times 50. We used this table last time. First column called ZX. One column called Phi M plastic or ML. There is another column called LP and LR. So from this table, I can figure out what is the lengths LP and LR based on your cross section. If your unsupported length of your compression flange in between, that means we are under the effect of lateral torsion buckling, and we need to calculate your nominal moment based on this equation. CB time M plastic minus M plastic minus 0.7 FTL SX time LB minus LP divided by LR minus LP. All of this stuff times CB, and this term must be smaller than or equal MP. Your equation becomes more complicated because the first case, your cross section is compact, everything is good, just only M nominal moment equal F yield times ZX, that's all. But if your cross section is non-compact and you are we have issue with lateral torsion buckling, which means your unsupported length in between these two values, then your nominal moment becomes more complicated using this equation. CB is a factor based on what type of fluid, concentrated, one concentrated, two concentrated, three concentrated, or distributed. Also based on what is the point of support in your beam. If your beam, for example, this part is hard a little bit. CB, if your beam is simply supported with one concentrated load, and your beam is supported by vertical bracing only at the first point and the end point, your CB equal 1.32. If your simply supported beam with one concentrated load is braced by vertical bracing at these ends and intermediate point, your CB equal 1.67. If your beam under the effect of two concentrated load and your beam is supported by vertical bracing at this location, then your CB in this part equal 1.67, in this part equal 1, in this part equal 1.67. It's complicated a little bit to use this one. Actually, we have another option. We can neglect this equation, forget it, and use another equation. This one. Phi Mn, your design moment directive, equal CB time phi M plastic minus phi BF time LB minus LP. Or design can be done using the chart. Design. Here is the table of design of B. Based on what is the name of your cross section, I can figure out what is the value of Zx if you would like to use this equation only. And also can tell you what is the design moment phi M plastic direct according to LRFD in Cape feet, and also can tell you what is the LP and LR, these two distance. You can make comparison between your LB and these two values. I would like to write this equation first. We have another equation here. We are in this case your LB in between. So your design moment phi Mn equals CB time phi M plastic minus phi BF time LB minus LP. In this case, if your LB greater than LP, smaller than LR. Whatever. Go back one more time to your table. Phi M plastic. Where is this term? Phi M plastic minus phi BF. Actually, phi is 0.9, BF is here. So based on your name of your cross section, I can figure out what is the value of BF. LB minus LP. You know LP, the first one. The second term, LP, can be given from this table. So if you would like to use this equation, that's fine. If you would like to use this equation, that's fine. Every single term can be selected from table based on your cross section. I prefer to use this one. It's more simple than this one because we have here many terms, but this one is more simple. Or we can use chart. This chart is available in the handbook of FE exam at the end of this one. This chart is very, very, very simple than using the equation. How? Okay. Let's see. We have wide 14 times 21 cross section. And this beam has vertical bracing at interval LB equal maybe 10 feet. What is the design moment or design bending strength for this beam? Only one step. This scale, what is your braced length and supported length of your compression flange? 10 feet. So we are here at 10 feet. Go up until you hit this name of cross section, W14 times 21. Where is W14 times 21? Do you have it? We have here 14, 1461. Actually, we don't have. Okay, let's do it 61. So we have here this curve W1461. This curve will hit your vertical line. Go horizontally. Your design is around 375. Available moment, phi m, in a very single step. Just only using your braced length, which called LB, and name of your cross section, you can get your design bending moment in one step. I don't care you are in this case or in this case, everything is considered in this chart. So actually we have two options in your design. First option, we can use equations besides your table. The second option, you can use this chart. But this chart does not include all cross sections. Only few cross sections, not the whole cross section. So if your cross section not considered in this chart, we have to go back to your table, tables. Yes. Let's do some example. This example.
I have a question. Do you know where we can find Sx for the other equation?
Yeah, from table also.
From the table?
Go back to your table. Based on the name of your table, besides Zx, besides phi m plastic, you will have Sx. If you didn't find them in table of design of beam, go back to W-shaped tables. You will find Sx as section properties. Okay? We have a beam, simply supported beam, with span 30 feet. This beam, this steel beam, W16 times 31, steel A992. It supports a reinforced concrete floor slab. Wow. This beam supported reinforced concrete floor slab that provides continuous lateral support of the compression flange. That means your LB equal 0. Every single inch of your compression flange is supported by concrete floor slab. The surface dead load equal 450. Surface live load equal 550. Does this beam have adequate moment strength? This beam of W16 times 31 from this steel type can support this surface dead load and this surface live load? Can or cannot? So we need to make comparison between M ultimate and Phi MN. In your design philosophy, your M ultimate must be smaller than or equal your design bending strength. So, first step, what is your M ultimate from structure analysis? 1.2 dead load plus 1.6 live load. Dead load and live load is given. So 1.2 times 450 plus 1.6 times 550. What's your value?
1420.
1420 pound. We have something wrong. Your dead load equal 450 pound per foot as uniform distributed load. Your live load equal 550 as uniform distributed load. Pound per foot. Pound per foot. That means your ultimate uniform distributed load equal 1420 pound per foot. We still need get you to calculate your moment. Equal WL square over 8 because your beam is a simply supported beam under uniform distributed load. Remember, the given surface dead load, surface dead moment. So 1.2 dead plus 1.6 live can give you the W ultimate. 1420 time L square 30 square divide 8. What's your value?
159,750.
Say it again.
159,750.
Pound foot. Can you multiply, divide it by 1000 and multiply it by 12? So 15975 divided by 1000 times 12 to be in kip inch.
1917.
1917 kip inch.
1917.
19, yeah. So first